Welcome everybody to lecture number 11 from the Summer School on Dynamic Deformation of Solids, hosted by CREDDS. Today's lecture will be on hydrodynamic instabilities, presented to us by three lecturers, Ye Zhou, Robert Rudd, and Bruce Remington, who are all from the Lawrence Livermore National Laboratory. It's a very distinguished cast. Dr. Zhou got his PhD in fluid dynamics and plasma physics in 1988 from the College of William and Mary. He's an APS fellow, Associate Director of Computers and Fluids. Robert Rudd got his PhD in theoretical physics from Princeton in 1992. He is the winner of the Gordon Bell Prize, and he's a fellow of the APS as well as the IOP. Parenthetically, that prize that you got, I believe, was for molecular dynamics of turbulent mixing. Am I right?
That's right, yes.
I remember that because I visited Livermore right around that time, and Vasily Bulotov pointed it out to me. And then we have Bruce Remington, who got his PhD in heavy ion nuclear physics from Michigan State University in 1987, and he is, among many other awards, the Edward Teller Medalist, which is a big deal, especially at Lawrence Livermore. So we are very glad to have you join us today, and with that, I hand it over to Ye Zhou.
Okay, thank you, Michael, for that introduction. Good afternoon. So today I'm going to start by talking about hydrodynamic instability to give you an introduction. Then I will follow by two of my esteemed colleagues here. So when we talk about hydrodynamic instability, usually we talk about three instabilities: Rayleigh-Taylor, or the RT, Rackman-Meshkov, or RM. These two instability I'm going to talk about first, then I will talk about carbon-compost instability a little bit later. So for the RT and RM instability, usually they are characterized for a period of time by this kind of mushroom type of structures with the heavy and the light fluids separate them. So you can see these kind of structures in many natural phenomena. For example, if you look at this picture, took off the clouds by a professor from UCLA, then you can identify many of these kind of structures. So as a matter of fact, Lord Rayleigh, in his study of around 1883, so he started by studying the Rayleigh-Taylor instabilities by observation of the clouds formations. So the physics of this kind of instability actually is fairly easy. So here I have a sketch on how the Rayleigh-Taylor instability started. So you have some heavy fluids on the top with a higher density, and you have the light fluids a little bit lower here with a lower density. And they are separated by some kind of interface between them. And for the simplicity's sake, we can assume that there's a sine wave type of shape. But obviously for applications, they are more complicated than this. So then you apply some kind of gravity or some kind of acceleration here, then the instability is going to grow with this kind of evolutions. Then the heavy and the light fluids are going to start to mix. So there's a very few occasions we can actually connect science and technology. It's beautiful kind of artwork. So we are not going to miss opportunity here. So here's this kind of painting technique called the accidental paintings. It's actually very much close to the Rayleigh-Taylor instability I just described to you. So you can actually try this kind of accidental painting technique at Thomps. So what you do is you take advantage on the different density of the different color of the paints. So in this illustrated example, in this sequence, what you do is you first pour some kind of black paints, then you are on top of this, then you pour some white paints, then you form these kind of structures. Then you just wait and let the gravity to take action. Then eventually you will generate this kind of beautiful kind of patterns. You can observe this in this kind of beautiful murals. Okay, so the Rayleigh-Markov instability is the second instability I'm going to talk about. As I already mentioned, RM instability is very close to the Rayleigh-Taylor instability. Actually can be viewed as an impulsive counterpart of the Rayleigh-Taylor instabilities. So here, to take a look at the physics. So again, you have the heavy and the light fluids separated by some kind of interface. Again, is some kind of a sine wave to start with. Then instead of apply the gravity as what you do for the Rayleigh-Taylor, what you have is you have a shock wave to pass through the interface. So this obviously is the impulsive actions, and it's going to generate, again, this kind of mushroom type of shapes. So for most of the instability I'm going to talk about today, basically they are undesirable. So it's going to cause you a lot of problem. I will give you the example a little bit later. But for some of the exceptional case, such as a scramjet, so this kind of instability actually is going to be very welcome. And there are several studies have demonstrated if you apply the RM instability correctly, it's kind of right kind of the applications, then the RM instability can enhance how well the fuel and air are going to get mixed together. So that's going to improve the performance of the scramjet quite a bit. Okay, so one of the most famous example, a lot of you have seen these pictures. So that's a picture about the Crab nebulas. So Rayleigh-Taylor instabilities, so are the proposed origin for this kind of filament. You can see from these kind of pictures. So it's actually it's a heavy fluids, as I described to you before, will form these kind of fingers, so they stream downwards. And in the meantime, the light fluids will form bubbles rising between the fingers. So again, if we look at this kind of picture, as I point out already, if you look at these kind of mushroom shapes with heavy and light fluids with the different densities, then if they start to move, then this kind of having this kind of rollover type of shape, then because you have the different velocity and these two fluids, heavy and light fluids with a different density, then that's the cause of going to give you so-called carbon composite instability. That's the third instability I'm going to discuss with you. So just to be a little bit more precise, so what's a carbon composite instability? So you have two layers of the fluids with a heavy and light fluids with a different density, obviously, and with some kind of interface here. So if they travel with a different velocities, then that's going to lead to the carbon composite instability, KH instability. So probably you have seen this kind of picture yourself or from the web. So for the carbon composite instability, it's characterized by this kind of beautiful roll-up type of shapes, sometimes going this kind of trends with a lot of these things. It's a very beautiful pictures. And clearly, you can reproduce carbon composite instability from the laboratory settings. And this is one of the experiments in the laboratories. And the connection of the carbon composite instability to the Rayleigh-Taylor or Rayleigh-Markov instability is, as I already mentioned, when you have this kind of mushroom type of structures, when you have the rollover, this kind of development, then they are going to cause you to have the Helmholtz instability. And they are basically going to play a big role for this kind of flows to eventually to transition to turbulence. So I'm going to talk about that a little bit later. But let's go back to the basic to see how we study, how can we study the Rayleigh Taylor instabilities. So we can start from the beginning, and here is a laboratory experiment with a different time sequence of the Rayleigh Taylor instabilities. So you can see from the early time, you have the different fluids with a different density, and obviously you have the gravities with the small perturbations. As time goes, eventually you are going to develop this kind of mushroom type of shapes. So for the early time, with some kind of limits on the amplitude, so we can write down the equation for the amplitude of the growth very easily. So let's say A is amplitude of the Rayleigh Taylor growth. So this second order derivative equation is given on the right hand side by A itself. G here is a gravity, and the K is a wave number, which is defined as the inverse of the wavelength. And A is the important parameter called Au number, basically the difference between the heavy and light fluids plus normalized by its sum. So when you have this equation, it's very easy to see the growth rates, but that's basically the solution of this equation is given by the square root of G times K times A. Again, it's a gravity, inverse of the wavelength, and the Au number. That's a density difference. So the solution for this problem is for the amplitude is equal to any of the initial value A0 is grown by exponential of this growth rate times the times. So this equation really just demonstrates why the Rayleigh Taylor instability is so important, because this instability can make the perturbation growth much bigger in a very high speed, actually initially go the exponential forms. Okay, so let's see how we can treat the Rackman-Meshkov instability. As I already mentioned, so they can be viewed as a RT instability, but with a gravitation force is impulsive. So in this case, then we can just easily replace the gravity by the product of the velocity jump times delta function over the time, because that's impulsive. And delta U is a velocity jump across the interface, obviously caused by the shock wave. So then the governing equation for the amplitude growth is given by these equations. And the solution, very important, is the amplitude growth. In this case, is a linear in the early time rather than the exponential for the late time, like Rayleigh Taylor instability. Okay, so in the real applications, so it's very hard to have the initial condition go as a sine wave, right? So that's why in the initial condition in many practical cases, so they are multi-modes rather than the single modes, like I described to you. And also, so this kind of instability growth, they are not only limited to the linear regions I just talked about. Actually, they continue to evolve, going to the nonlinear, from the linear going to the nonlinear, then eventually with the help of the common Helmholtz instability, going to become a turbulent phase. So here is just a different snapshot of a Rayleigh Taylor experiment for different time. So this is the early time, obviously in the linear regions. And if you wait a little bit later, it becomes highly nonlinear, then eventually we'll transition to kind of the turbulent regions. And on the right-hand side, you can see here is a Rayleigh Taylor simulation carried out in Livermore. So if you separate the spike side and the bubble side, then you can see the flows is very highly turbulent with a lot of mixings with a large structure and small structures. Very beautiful. And the same story is true for the Riemann-Maskhov instability. So here is a sequence of the pneumatic summation for the RM instabilities. So it's very similar to Rayleigh-Taylor, but in a lot of these cases, there's additional complications. When you have a shock wave, such as the shock wave in a shock tube, so then the shock wave going to bounce back from the wall of the shock tube and going to hit the interface the second time a little bit later. So that's often called a reshock. So that makes the interface, the mixing layer, much more turbulent to become turbulent much faster. So basically the reshock going to speed up the transition process to turbulence. Okay, so then you see why we care about the turbulence, why we cannot just stay with the linear and nonlinear phase. See, the problem is in a lot of applications, we cannot avoid them because turbulence play a very important role and they have a huge impact on the mixings. But this makes the problem extremely hard. The reason is that turbulence has been a subject of study for many, many years. So actually you can go back to this illustration of the turbulence flows by Leonardo da Vinci about 1500s. So da Vinci obviously not only was a great artist, but also he was a great scientist. So here you can see it's a very, very precise visualization of turbulent flows past the object with the different orientations. So it's very extremely beautiful work. So sometimes people say his drawings were the first scientific visualization of the turbulent flows. Now this when we have to deal with the turbulent flows, so then we have different dimensions. So in the middle of the view graph, you can see this is a turbulent jet experiment carried out in a laboratory experiment. And here is a rocket engine test outside of Los Angeles. So you can see there's a big difference in terms of the spatial dimensions. So in the laboratory experiment, so we are talking about 10 centimeters. But when you're talking about the rocket engine test, we are talking about hundreds of meters. But if you compare the visualization of these two images, despite this big difference in the length scales, so you can see there's a very similar kind of structures. So in fact, this scaling relationship you can use to study the many experiments in the laboratory frames. I'm going to talk about that a little bit later. So let me just say one more connection about the astrophysics phenomenon and art and the turbulence. So here on the left is an image taken by Hubble telescope for distant stars. So when this picture was taken, then a lot of people immediately noticed, both NASA and the American Museum of Modern Arts, they noticed this kind of pattern look like this. There's a lot of similarity and assembly to this kind of Van Gogh's pictures of the starry light with all these swirling motions. So there's a lot of commentary in the media about this. But we actually, this kind of artwork actually has something to do with turbulence or not. So actually several scientists actually carry out a study on a number of Van Gogh's pictures by digitize the luminance of the Van Gogh's pictures. Then they carry out the statistic studies of the luminance with the same kind of methodology as what you do with the data obtained from the wind tunnel experiment. So that's given by the picture on the right. So the conclusion what they have is if you just compare the statistic of the luminance in Van Gogh's paintings, they do contain the characteristic fingerprints of the turbulence flows. So I thought that's very interesting. Okay, so let's talking about the Rayleigh Taylor Rackman Meshkoff instability. As I already talked about the scramjet. So that's one of the examples. The instability is very highly desirable because that can improve the performance of the engine. But in a lot of cases, it's very unwelcome. So one of these important situations is this inertial confinement fusion, or ICF. So this is a lot of work is try to achieve the ignition. Then if we can do that, then we are going to have unlimited clean energies. So the idea of this, let me just give you a quick summary, is to starting by some kind of capsule with some kind of abrader. So that's outside layer. Then you have another layer, and you have a bunch of the fuel inside. So what you want to do is to use laser beams to either do a direct drive. So that means you apply all the beams in a symmetric forms on this target, try to drive the system to achieve the ignitions to get the fuel to ignite. Then alternative method is so-called indirect drive. So you have a horon, usually is made by gold. Then rather than to apply the laser beam directly to the target, what you do is you apply the laser beam to the side of the horon, then to generate a very intense X-ray laser to drive the capsules. So when you have the external shock wave or the drive into these kind of systems with a different layer of the densities, then from the description of RT and RM instability, and you know we are going to have this kind of strong hydrodynamic instabilities. So that usually is a trouble, because once you have the mixture between the different materials, between the heavy material inside the fuels, that's going to cool off the temperature inside, prevent you to have the high energy production from these kind of systems. So on the right here is just a figure for me to illustrate this effect. So on the x-axis is a mixed mass. So that means the bigger the values, that means you have more mixtures. So you can see on the y-axis is energy production characterized by neutron year. So obviously the bigger has the mass, then this energy production going down. So that's extremely unwelcome, and a lot of work have been put in to reduce this kind of effect. Now, the astrophysics, so the instability is very important. So there's a lot of news recently also about the different supernovas. So the Rayleigh Taylor instability is really a key component to make any of the supernova to actually go off. So two of the supernova, they have classified into two different types. So for the type 2, so that's a supernova core collapse. So usually these are very big, big size stars, about 18 or 19 solar mass. So just before they collapse, then you can see they form this kind of awning type of structures. It's a different layer of the materials. Obviously, they have the different densities. So when you have the core collapse, so then this is basically a sequence on this core collapse activity. I don't have time to go into the details, but except to point out the turbulence mixing is a key is involved to explain a key process to restart the star shock for this core collapse process in order for the supernova to go off. So if we look at the other type of supernova, the supernova 1A, so that's a very different kind of supernova involved with a lot of thermonuclear burning with the flames. And again, the hydrodynamic mixing is very important for the detonation process in order for this kind of system to go off. Okay, so in the Livermore and a lot of different place. So there's a big effort to study the astrophysics phenomena in the laboratory setting with intense laser systems. So my two other speakers are going to talk a lot of experiment. So here is a National Ignition Facility in Nif in Livermore with 122 laser beams. So a lot of efforts are trying to do the core collapse supernova experiment with a very large dimension. So you can see we go to the thousands kilometers with a time scale about 100 seconds. You want to do this kind of a large size process with such a small laser target, then this kind of simulation going to only go about 100 microns with a time scale about 10 nanoseconds. So here is one of the example on how this come about. So on the right, extreme right, this is the image about simulation for the core collapse supernova explosions. Then again, you can see this kind of beautiful mushroom type of shape coming out with the instabilities. And this image here is for the hydrodynamic implosion experiment. Then you can see again, you can see the similar kind of structures. You can reproduce the effect in the laboratory settings. And the way to make connection is through this kind of rescaling process. My speaker, Bruce, made an important contribution to this. Then obviously, on the laser platform, you can study the Rayleigh-Taylor, Rackman-Meshkov, and Kalman-Helmholtz instability in great details. Then you can do this kind of experiment just to isolate the physics. So here is a time sequence of an experiment for the Kalman-Helmholtz instabilities. You start from very small perturbations with a velocity traveling with a different velocity with a different density of the two layer. Then eventually you can see, you can observe this kind of characteristic Kalman-Helmholtz instability rollover structures. Okay, so what kind of external factor can influence the growth of the instabilities? So there are several different examples. So one is the system rotations. So here is a pneumatic simulation of the Rayleigh-Taylor instability at a later time without the rotations. So you can see you have large structures and you have the smaller structures. But when you have the same kind of Rayleigh-Taylor instability subject to a strong external rotation, then you can see you dump out all the small scale structure, then you only have some large scale structure left. So the same is true in the situation Rayleigh-Taylor with a magnetic field. So if you don't have the field, again, you can see there's different large motion and the small motions. But if the same kind of flows subject to a magnetic field, then you can see you will only have the large structures. You don't have small scale motions. And the same is true for the high energy density, high energy flux. And this is the growth of the mixing layer measurement. So for the blue curve, it's when you have a low flux. Then for the red curve data is for the high flux. So you can see when you have the high energy flux, obviously you have a smaller mixing layer growth. So you suppress the instability growth. Okay, so let me, before I conclude, let me just talk about the importance of the viscosity and the growth of the instabilities. So to demonstrate this effect, so let me show you the two calculations. One is on the lower right, is this inviscid calculation. So that means you are doing a calculation without the viscosity. Then you can see these are large scale structures, and also you have a lot of small scale motions. So that's very, very interesting. But if you perform the same calculations, but turn on the viscosity, then you can see all the small scale structure get damped out, then you only have the very large scale structure left over here. So that means the viscosity has a very important effect on depressing the growth of the Rayleigh-Taylor or Rackman-Meshkoff instability. So here is just some kind of formula I'm going to put here without going to the details, just to point out for both Rayleigh-Taylor and the Rackman-Meshkoff instabilities. So the higher viscosity, the lower the growth rate. And in addition, I'm not going to go to the detail about this equation. There's also a dependence on the wavelength. The shorter the wavelength, you have a bigger effect from the viscous motions. So this kind of equation, the effect of the viscosity, give us a crude segue to the solid state trends in the plastic flow regimes. And that's the subject my two colleagues are going to tell you a lot more details. And these are something people sometimes call effective lattice viscosity. So these are very interesting topics. And you are going to learn a lot from the next two presentations. So before I forgot, I just want to mention all these details are contained in several papers. We have the review articles, and you can check out if you are interested. Thank you.
Thank you very much, Ye. So I suggest that we hold our questions until all three speakers have had a chance to present. So I believe our next presenter will be Robert Rudd. Yet, in order for Robert to go, you're going to have to press the stop presenting button on your screen.
Okay.
Perfect.
Sorry, had to turn off the mute before sharing the VRAS. Okay, can you see my view graphs?
Sure can.
Excellent. Okay, so it's a pleasure to be here as part of this really outstanding lecture series. So I'm going to carry on the discussion of the hydrodynamic instabilities, but now turning to solids. And in solids, there are analogous phenomena to all of the instabilities that you described. So, for example, let's see. With Rickmeyer-Meshkoff instability, so there are these beautiful structures that form in fluids. If you look at solids, such as this double shock 10, again, you get these very dramatic instabilities developing at the interface. For fluids in shear, you get the Kelvin-Helmholtz bellows forming, such as these roll-ups that are seen over Mount Shasta. In solids, if you have two metal plates that come together in an oblique impact, you get the Kelvin-Helmholtz instability forming at the interface. And in this case, it's important for the industrial process of explosive welding, so that the roughening that forms at the interface is part of what helps lock the materials together. For Rayleigh-Taylor, so again, in solids, it's observed. So this is an old experiment due to Barnes et al. And what's shown here is an aluminum plate viewed with radiography from the side. And down at the bottom at time 0, you can see there's just a very small ripple on the surface. And then an explosive drive sends a plasma across a gap that stagnates on the surface. And that ramp loads the interface and accelerates it. And so you can see at later times that what were very small ripples initially have grown considerably. And a similar experiment more recently done with tantalum, again, you see substantial growth of the ripples over time. So this growth factor is the ratio of the ripple amplitude at a given time to its initial amplitude. And so you can see the ripples are growing dramatically. So both in a relatively soft and a relatively strong metal, if they're driven hard enough and the Atwood number is positive, you can get substantial growth of perturbations. So, I think intuitively you might have expected, well, solids are strong, they're going to resist that growth. And indeed, the strength of metals and materials, suppress the growth of the perturbations to some extent, but they don't completely suppress it. And this insight was taken up by Bruce Remington a couple decades ago, and he's developed the notion that not only does this instability happen in solids, but it can actually be used to investigate the strength of these metals under extreme conditions. And this turns out to be a very nice platform for doing that because you can look at the strength effects in uniaxial compression. But here, because the ripple flow perturbs the development of plasticity, you can actually get substantially larger plastic strains with a rippled surface. And so it decouples the strength from the equation of state of the material. And so it lets you get really nice measures of plastic strain at high pressure. So through the course of this talk, I'm going to touch on a number of things. So one, I'm going to revisit this question of the theory of the Rayleigh-Taylor instability, both in viscous flow and for elastic plastic materials. And then I'm going to look at some of the constitutive models that have been used to understand Rayleigh-Taylor experiments at extreme conditions, looking at both rate-independent and rate-dependent models in these dynamic experiments. And of course, part of this is kind of, what you've seen in many of the previous lectures, that plasticity, it's a multiscale phenomenon. It originates with the strength of bonds and then it percolates up through the length scales to affect flow at the continuum level, such as in our rippled sample. And so the experiments probe at that continuum level, but they tell you things about plasticity throughout it, but you have to rely on models to make that connection. So ultimately, you get data that looks like the radiography, the face-on radiography shown at the bottom, and then it's compared to models in order to understand what's going on with the strength. And so I'll say a bit more about that connection. Okay, so first, taking up where you left off, you can think about the effect of viscosity on Rayleigh-Taylor perturbation growth. And so this has been studied for, well, since the early 1900s. What people have found is that viscosity, if you have a fluid, a viscous fluid, the viscosity suppresses the growth, but it doesn't cut it off entirely. The system still, if the number is positive and it's accelerated, the system is still Rayleigh-Taylor unstable. And so, for example, in this plot of wave number versus the growth rate, for the viscous curve, you see that, well, at long wavelengths, so that small wave number, you get this kind of classical suppression of the growth. But then classically, what would lead to very high growth as the wave number increases, the curve turns over due to viscosity, and the viscosity suppresses but doesn't completely eliminate growth at the short wavelengths. If you consider surface tension, it actually does cut off the growth, and at sufficiently small wavelengths, the system is stable against the Rayleigh-Taylor growth. So you can take this kind of viscous description and apply it to metals, such as what's shown on the right here. So these are data from an experiment done at the Omega laser. that accelerated a rippled vanadium sample and then observed the growth of the ripples. And the two blue squares are experimental data with different ripple wavelengths. And then plotted against that are curves from a number of different simulations using different amounts of viscosity. And so the classic growth is up at the top. And so, you see this kind of growth that as you go to shorter wavelengths becomes very large. If you just have, say, liquid viscosity, the growth is basically indistinguishable from the classic growth on this plot. But if you crank up the viscosity, what you see is that at some level you start to get agreement with the solid response. And this is similar to things that you've heard in previous lectures. Here in this viscosity model, it has an exponent of 1, which limits its range of applicability, as you've heard in previous lectures. But it enables you to get at kind of the heart of the phenomena. And you can notice that, well, for say the 400 poise response curve, there's now a maximum in the curve that occurs at 80 microns, and you get measurable growth even at the shorter wavelengths. So 400 poise is a very high viscosity. So this is, say, 4 orders of magnitude greater than what you'd have in a molten fluid. So it's an enormous viscosity, and yet that is what was found, in this set of experiments across a number of different delay times and wavelengths to give approximately a reasonable description of the response of the vanadium. Now, if you zoom in to shorter wavelengths and reduce the time, you can see what kind of a molten fluid would give. So now you'd have the maximum wavelength or the wavelength of the greatest growth is down at 0.2 microns, so substantially smaller wavelength, and it's growing much more rapidly. So you have to look at earlier time to be in kind of the linear growth regime. So in fact, if you go through the analysis, this most dangerous mode grows like the viscosity to the 2/3 power. And similarly, if you include surface tension, there is actually a wavelength at which the perturbations no longer grow, and that's because with surface tension, it resists the curvature of the interface, and that actually suppresses the flow. But we're not going to really worry about that for solids. Okay, so to go beyond just a simple viscous description of metals, you could look at a kind of conventional, say, elastic plastic response, as was familiar with observations from mechanical testing, where initially the material deforms elastically, and then you get plastic flow with hardening. So people have used similar models to do analysis of Rayleigh-Taylor growth. So in this work by Perez et al., they were looking at the response, the elastic response of a solid up against a fluid. And what they found there was that, again, with wave number, the curves are turning over. And in fact, that there is a critical wavelength in a purely elastic solid beyond which the growth is stable. Similarly, they have also looked at the effect of, say, Rayleigh-Taylor instability in an elastic plastic solid. And here it's kind of a response plot, wavelength and initial amplitude, and they get different regions of response. So for sufficiently small amplitude and a sufficiently short wavelength, the system is stable. So it's an elastic response and the system is stable. If the amplitude's a bit greater, but still the wavelength short enough, the system is still stable against Rayleigh-Taylor growth, but it's now undergoing plastic deformation. And so by stable, what I mean here is that the acceleration happens, the amplitude of the perturbations starts to grow, but then it oscillates. So it doesn't grow exponentially the way that it does in the unstable regime. But for a sufficiently large amplitude or a sufficiently long wavelength, you do get unstable growth in plasticity. Now, so we're going to be interested in these kind of laser-driven Rayleigh-Taylor experiments. And for them, say the critical wavelength, for example, in the vanadium Rayleigh-Taylor experiment I was talking about, is about 50 nanometers rather. And that's much less than the amplitudes that were used in the experiments. So the experiments are above this critical amplitude, and they do undergo unstable growth. Also, in the ramp loading, there's a leading shock, and typically the amplitude of the leading shock exceeds the Hugoniot-elastic limit. So you recall from previous lectures that means that it's in the post-shock material, it's deforming plastically rather than elastically. So we're really interested in something that's more of a viscoplastic response in these experiments. So, so from the previous lectures, you'll recall that you do have this kind of multiscale phenomenon in plasticity. But what you really want for these experiments is something that you can run within a continuum hydrodynamics simulation that will tell you how the material responds to the various driving forces. And so there have been a number of models that have been applied to these systems. So I'm going to focus on 5 of them just to give you a little bit of background so that you'll understand, as those are paired to experimental data, what's being learned there. So the simplest of the models is the Steinberg-Geynin model, and then the improved Steinberg-Geynin model. Both of those are rate-independent models. And then the Steinberg-Lund, Preston, Thomps, Wallace, and Livermore multiscale models are all rate-dependent models. And I'll say a bit about those. So the thing that's different here from the previous lectures is that these experiments are typically done at very high pressures. So pressures that are comparable to the pressures at the core of the Earth. So say, a megabar to several megabars of pressure, where 1 megabar is 100 GPa. So these are quite large pressures. So accounting for pressure hardening is important. And of course, pressure does induce hardening in materials typically. So the bond strength is getting larger as the material is compressed. And so you get a strengthening as the pressure is increased. And some of these experiments are also done at significantly high temperatures. And so there you need to account for thermal softening. So the Steinberg-Geynin model does that by saying, well, the shear modulus itself exhibits pressure hardening or pressure stiffening and thermal softening. And so we can model the shear modulus basically with a linear pressure and temperature response. So that's these terms. The P here is the pressure, the T is the temperature. This term is modified slightly, the linear pressure dependence, by eta to the minus 1/3. Eta is the compression, so the ratio of the density to the initial density. And so what this does is it gives it the right limit under high compressions to agree with Thomas Fermi. And so that was what is done in the model. So it's at sufficiently high pressures, it's no longer strictly linear, but at lower pressures, it's linear. And so then the ansatz is that the flow stress has the same pressure and temperature dependence as the shear modulus. And this isn't strictly true in materials. There are lots of cases where the pressure dependence of the different contributions to plasticity come in differently, and you don't get this kind of simple relationship between the shear modulus and the yield stress. And but as a first attempt, that is what they did. And then they added in a strain hardening dependence, and then they could measure the shear modulus, and they could do impact experiments to get at the hardening. And so this was all calibrated at strain rates of, say, 10 to the 5 per second. So it's a fairly simple model. going from there, so one of the things that you might worry about is at these very high pressures, maybe that linear pressure dependence isn't right, and especially materials that are undergoing phase transformations. And so you could say, well, you know, we're not completely helpless here. We can get some guidance from first principles calculations from density functional theory and quantum molecular dynamics, which have opinions about the shear modulus. And, you know, in a multiscale sense, they can even go beyond that. But already, you know, with the density functional theory, you can say, well, you know, maybe we have an ansatz of what the shear modulus should be. And so that's the motivation for this improved Steinberg-Geynin model. And so here, you know, so for example, looking at vanadium starts out in a BCC alpha phase, but then it undergoes a transformation to a rhombohedral structure and then a different rhombohedral structure before going back to BCC at higher pressures. So within each of those phases, you can calculate the shear modulus appropriate to that structure, appropriately homogenized over some polycrystalline structure. And then you can combine them with some transition functions to get the shear modulus across a broad range of compressions. And here it really is expressed as a function of the density. But if you plot it in terms of pressure, it has a similar kind of structure where you get interesting things happening near the phase boundaries where there's kind of a martensitic instability going on. Okay, so, but going beyond rate-independent models, there's the Steinberg-Lung model. So this basically extends the Steinberg-Geynin model. So again, you have this familiar link between the shear modulus and the flow stress. But now there's a thermally activated term that brings in a rate dependence. And this particular form is one that they got from Hogan Mukherjee. And so it introduces some additional parameters and describes the rate dependence, and they were interested in extending the model down below the rates that the Steinberg-Geynin model is calibrated for. But you can do even better than that. So the Preston, Thomps, Wallace model is another rate-dependent model. So in this case, it's formulated around kind of asymptotic limits. So, so there's a formula for a yield stress that's introduced where, you know, as the stress needed to first cause the material to yield, and then a saturation stress, which, you know, as the material is deformed, eventually the plasticity will saturate and the stress will not exceed that. So then a temperature and rate dependent form that captures thermal activation is used for each of those, and then the total flow stress is expressed as kind of a Bochy instantiation of, you know, interpolating between those limits. So this now has a nice rate dependence to it. It's further extended with some descriptions of what happens in shock waves. So it's a nice model that expands a large range of rates. So to go beyond that, there's the Livermore multiscale strength model. And here, again, there's a set of equations that describes the response at the continuum level, including a rate dependence that comes in, again, in kind of a saturation form. I'm not going to go through this in detail other than to point out that in this case, the way the model was constructed was that each of the parameters in the model was determined from first principles by calculation. And so this is another strategy. So far, it's only been developed for a few materials like tantalum and vanadium. But let's see how these models compare to experiments. So here are shown some results from a tantalum Rayleigh experiment, again done on the Omega laser. So it's a laser-driven ramp loading. And so data were acquired at various times. So the radiograph was taken in flight, you know, as the material was deforming and the ripples were growing. And this is plotting, you know, the time of exposure of that radiograph and the growth factor. So this again is the ripple amplitude divided by its initial amplitude at a given time. And so there was a large set of data that were collected across a number of different kinds of material. And so here you see kind of the response that you'd expect, that but if there's no strength, then there's nothing that kind of impedes that shear flow, so you get a large growth. And then as the different models are applied, in these continuous curves, Steinberg, Geynin, Preston, Thomps, Wallace, Steinberg, Lund, and the Livermore multiscale strength model, as the strength increases, the growth comes down. And in fact, you see that the LMS model is in quite good agreement with the data. And this is true kind of regardless of the grain size, which was kind of an interesting result of these experiments, that you could go from a quarter micron grain size up to the grain size of about 100 microns, and you don't see the conventional Hall-Petch relationship. And we think we understand why that is, because the dislocation density is so high. So, in these simulations, you can go better than just, comparing to the data. You can go in and see, well, what's actually going on in the sample during these deformations. And so all of the models will tell you about the plastic strain rate, and you can see that, yes, indeed, the ripples are perturbing the flow field. And, as the ripples are growing, the material is deforming plastically to accommodate that growth. You can look at the temperature and see that, yes, it's well below the melt temperature. So, so there's a reason why the strength is different from a fluid. And in a model like the LMS model, you can go in and interrogate what it thinks is going on in terms of the microphysics. So the dislocation density and the dislocation velocity as a function of position and time through the sample. So that's very nice. So then you can say, well, this kind of experiment can be used to validate strength models, but what in fact are you validating there? So it's beneficial to go in and look at kind of what's actually being tested within the model. And what you see is that these strain rates of, say, a few times 10 to the 7, in the LMS model, the term that dominates the flow stress is the work hardening. So you might say, well, wait a second. We heard in earlier lectures through the activation volume analysis, through for BCC metal, really it's the lattice resistance that should be dominating. But the story is different here at these extreme conditions. And the reason is that the dislocation density is much higher. So the length scale of the dislocation network has reduced, and the temperatures are higher. So the lattice term is reduced. And so you end up getting work hardening domination followed by thermal activation. And even though these are very high rates, the phonon drag contribution is relatively small. In PTW, here too, the model says that the thermal activation is dominating over the drag. And the way the model is constructed is a little bit different. So exactly how the work hardening is being done, it's a little bit tricky to disentangle. But you can see that, here too, you're testing a particular part of the model by doing experiments at these rates. And with Steinberg-Geynin, it's rate independent, so you just have a flat curve and there's not a lot of structure to it. It turned out that this one comes in weaker than the other two at these rates. So, so that's all I wanted to cover, and I'm going to turn it over to Bruce.
Thank you very much. So don't forget to stop presenting. Perfect. Bruce, I don't know if you're speaking now, but you're muted. That looked good on my end when you did the presenter mode. Bruce, are you trying to go into presenter mode here? Is that what you're trying to do?
I unmuted. I'm going to have to quit and come back because I have, wait a minute, I have two windows open. Hang on. Can you hear me?
Yes.
Can you see view graphs?
Not yet.
How about now?
Yes. Yes.
Okay. How about now?
Yep.
Okay, so we can start?
Yep.
Good, sorry. Okay, so I'm the third speaker in this set of three, and I'll be talking about primarily experiments, testing the various concepts, physics and science concepts you've heard Ye Zhou and Rob Rudd talk about. Most of what I'll talk about was done on the Nif laser, but there will also be some examples from the Omega laser and also from LCLS. The Nif laser is shown here. There's 4 images. Let's see if I can get. There's 4 images of the Nif, the laser bay, the target bay, inside the chamber, and then an image of actual chamber center during the time an experiment has gone off. We are also doing supporting and related experiments at the Omega laser, the Omega EP laser, and LCLS. Okay, starting out with one of the first Discovery Science, the Discovery Science program at Livermore is where anybody in the world can propose for basic science to use the Nif laser. And one of the first discovery science projects that reached a conclusion was the equational state study of carbon, where they used diamond foils at pressures and densities that match those at the cores of giant planets. The first experiment they did was up to 50 megabars in a diamond foil. You can see that was a cover story in Nature. It also was in the New York Times. And the two references of interest are on the bottom by Ray Smith in Nature and in Nature Astronomy. On the right-hand side, you can see how this is done. The Nif lasers are brought into a radiation cavity called the hole room. They convert to a thermal radiation temperature. A hole is cut on the wall of the hole room, and a planar sample is mounted there. And then of different step thicknesses, so when the compression wave breaks out, one can back out of that the stress density curve for the material based on analyzing the shock breakout followed by the particle velocity. And then with a sophisticated analysis, you can produce this figure on the bottom right, which is a plot of stress versus density. The experimental results are the thick blue curve and the data points going along that give the error bars. And what's interesting to note is the comparison to density functional theory. So density functional theory for the Hugonio is the upper red curve. And so clearly we are achieving higher densities at the same pressure or the same stress for the experiment because it's a ramp compression, it's not a shock. But also the comparison with density functional theory for the cold curve, T equals 0, is interesting because that cold curve shows two very distinct phase transitions. There's a kink in this curve down at 10 megabars, which is 1 terapascal. And there's a second kink in the density functional theory curve at 30 megabars, which is 3 terapascals. But you look at the experiment and there were no kinks at all. It was smooth all the way through. So that gave us the first hint that the kinetics of the phase transitions is happening on timescales that are not so different than the experimental timescale. So exactly how long it takes to go through a phase transition now can be probed in these high pressure experiments, as well as getting the compressibility. A key issue, going back to this first time, this is the first Discovery Science experiment we did, this blue curve. But a key issue was, do we really understand the phase of the material? Because you see, we did not see the notionally expected kink of a phase transition at 10 and 30 megabars. And so we were worried that maybe we don't really understand the phase of the material and don't understand our experiment. So it was essential to develop diffraction so we could actually measure the phases of materials at these high pressures experimentally to enhance our ability to test the theories and the simulations. So here's an experiment. It just happened to be, there's a nice experimental result for lead. And so the diagnostic that was built to do the diffraction experiments on Nif is shown on the upper left. It's called TARDIS, for target diffraction in situ. And on the sort of upper left side is where the physics package sits, and the lasers directly drive that and drive a ramp compression wave through it. Separated from the physics package is a separate foil, that's the backlighter probe. So the backlighter actually go through, they diffract off the compressed physics sample, and there's practically 2 pi coverage of image plate recording these signals, the diffraction signals, that can be turned around in these plots shown on the bottom right. So these are diffraction signals from an FCC lattice, an HCP lattice, and a BCC lattice with increasing pressure for lead. And you can see why those structures appear when you look at the predicted phase diagram on the upper right, where you can see for a ramp compression, which is this dashed gray curve, one starts out in the FCC phase for lead and then transitions into HCP and ends up in the BCC phase at the higher pressures, then stays there. And so the experiments show that we could actually measure those phases in the ramp compressed high Z materials. Therefore, we can identify phase transitions and phase transition kinetics. So when this experiment was done on the diamond foils, it indeed supported the experimental measurement, where the phase transitions that were expected were slow enough that they did not occur over this, say, 3 to 5 nanoseconds, that the team could hold the pressure up. Okay, so with the Nif, of course, one's urge will always be, well, let's turn up the pressure and see what happens to the warm dense matter at the highest pressures we can achieve. So in this experiment by Andrea Kritcher, Thilo Deppner, and a whole big team of people, what they did is they said the way to get to the highest pressures on Nif is that we have to enhance the ablation pressure with convergence. So the ablation pressure, normally the lasers come into a radiation cavity, convert to X-rays, and the X-rays drive the physics package, whether it's a planar foil on the wall or a spherical capsule in the center. But the ablation pressure for these conditions of, say, 300 EV temperatures is about 135 megabars. And so if you want to get well over 100 megabars, you need to go beyond ablation pressure. And so convergence then amplifies that. So the combination of 100 megabar pressures from the ablation pressure amplified by convergence allows us to study the shock compression of a solid plastic ball up to a gigabar. And you can see the convergence of the plastic ball here as the shocks come in. That's the dense region, it's dark. And then when it reaches at the center of the shell, you get this burst of radiation. And so over a 10 nanosecond time scale, this 1 millimeter diameter solid spherical ball is imploded, and we study the shock trajectory as it implodes. You can see in the bottom middle, the laser power versus time. So it was an initial step and then a ramp compression. Here's the radiation temperature going up to about 300 EV in the peak. And then the backlighter is delayed a bit to make the measurements at the highest pressures. And so now on the bottom right, you can see compression, density over initial density versus shock pressure over a whole series of experiments starting from about 1 to 10 megabars, ramping up to 100 megabars with another set of experiments with another members of the team, and then finally taking this all the way up to gigabar. And this last result was published in Nature. The blue curves were published in PRL a year or two before. The interesting thing about the highest pressures is that you can see the theoretical predictions at just below a gigabar starting to reach a peak in compression and then turning over as you start to ionize so many electrons into the continuum, so that the pressure from the electrons starts to reduce the compressibility. But during the time that you're ionizing out of the different shells, that softens the compressibility, so you get this predicted peak at around 500 megabars. And so we've now gone through that regime with experiments, and you can see those are the red curves, and then the blue curves or purple. So the red curves match the experiments up to about 500 megabars. Beyond that, we have experimental data, but the shock strength is strong enough that the radiative precursor floods the region ahead of the shock, preheats it, and the compressibility drops because of that preheat. And so even though our data continues on up, for what we published in Nature, we truncated it, I think it was right about 400 megabars. So that's a very nice result, pushing the limits of what you can do with the energy we have at Nif. Okay, diagnostics are critical, and trying to get a handle on the temperature under these conditions is really important. So over the years, both at the Omega laser and now on Nif, we've been developing the XAF's experimental capability. XAF stands for Extended X-ray Absorption Fine Structure. And what this does is has an external source of backlighter X-rays that are a smooth continuum, and we're then transporting that through the physics package that has been compressed with ramp compression, and then we look at absorption spectroscopy of the probe X-rays coming through, and by examining the features in the absorption spectra above the edges, we see these interference patterns that has to do with constructive and destructive interference of the electron wave function as it gets ionized from the bound state up into the continuum. And so that interference pattern actually is very sensitive to the temperature of the lattice. When the lattice is cold or cool, the interference pattern is very distinct because the electron wave function scattering off the lattice has a nice static lattice to scatter off of. But when the lattice warms up because of either preheating or because of just the compression work done on it, then there's thermal energy put into the lattice, so there's random vibrations, and that the interference patterns from the electron wave function, especially at the higher Ks, which is the shorter wavelengths, starts to be extinguished, and so these ripple amplitudes drop, and the period gets larger because K is getting larger because the electron energies are going up. And so we can analyze that to get temperatures out of the lattice under these extreme conditions. And so here's plots of temperature versus ramp compression peak pressure shown for two different shock strengths. For the lower pressure shock strength of slightly below a megabar, you can see the temperatures are lower. That's the top plot on the right-hand side. And then when the shock strength is increased to 150 to 170 GPa, you can see the temperatures are higher because of the added heat put in by the shock. And so now we have a way to actually measure those temperatures, which is very powerful. And it allows us to sort of finish the pieces that you need for the equation of state, because you'd like to understand pressure, density, and temperature. And temperature has always been the hardest to measure, especially in the solid state where the temperatures are low, so it's not emitting X-rays. Yet that's where some of the nicest new science can be done. So in this first experiment done by Yuan Ping et al., published in the PRL in 2013, they were surprised at how hot the lattice seemed to be, much hotter than what you'd get just from PDV work. And so they guessed that maybe there's strength in the lattice, and you're doing work against the strength as you compress the lattice. And so they then tested that concept and said, if the added temperature is coming from strength, work done against the strength as you compress, then from these temperatures, we should be able to back out an estimated strength. And so this bottom right plot on the bottom right-hand side shows the analysis of how much strength would be needed to reproduce the experimental data. Albeit there's large error bars, but nonetheless, it proved this concept that we do have a way to get to the strength separate or in support of the simulations, which also predict the strength. So we have now simulation capability tested against the various experimental diagnostics. In addition, we were able to test the strength directly from the experiment itself. So that was very powerful. Okay, now aiming towards Nif and higher pressures. This just shows hydrodynamic instabilities. You heard this is a hydrodynamic instability in the plasma state that you heard Ye Zhou talking about. So on the Nif laser, we just showed that we can generate very nice Rayleigh-Taylor instabilities in the plasmas with no strength. Side-on images show these beautiful roll-ups of Rayleigh-Taylor bubbles and spikes, and you see the tip broadening and the swirling happening. This is a Physics of Plasma paper by Sabrina Nagel in 2017. Once you zoomed in, you can see what is suggestive of looking towards a transition to the atomic mix, which was very nice. On the right-hand side shows face-on images of a plasma experiment, showing that we can put multiple wavelengths, on a single experiment, so that we can actually measure a dispersion curve on a single experiment. And so now when we take this to the solid state, this was an experiment shown also by in Robert Rubb's talk. So this is an experiment by Hye-Suk Park that was done on the Omega laser, I believe. One of her first experiments in this sequence of solid state Rayleigh-Taylor. This was for tantalum, and you see here's the hole rum. The Omega lasers come into the hole rum. They generate an X-ray drive. It launches a strong shock through a sacrificial piece of plastic, brominated plastic, and then this shock breaks out, a plasma sweeps across a vacuum gap and stagnates on the physics sample that you're studying, which is a rippled piece of tantalum, in this case, wavelengths of 50 and 100 microns. The bottom left shows an analysis of the pressure versus time for this experiment in tantalum, and there's a peak pressure of about 1.3 megabars. To the right of this, these are predictions from simulations showing what the predicted temperature in the tantalum physics sample should be compared to the melt temperature. So this technique of having a shock release from a shocked reservoir sweep across the gap, stagnate and push on this sample, much like the Barnes experiment, keeps the temperature about 1/5 of the melt temperatures. So this was a very robust platform for studying solid state Rayleigh-Taylor, with there being very little possibility of melting, because we're about a factor of 5 below the predicted melt temperature. And then this is the whole long sequence of experiments done by Ye Zhou on Omega, showing rippled tantalum growing at a wavelength of 50 microns, perturbation growth factors versus time. The predictions for a series of different strength models are shown by the smooth curves. So no strength is this cyan curve. Steinberg Geynin comes down a bit. PTW is about a factor of 2 or 3 below the no strength. Steinberg Lund a little bit more. But the Livermore multiscale model was in the best agreement with the experimental data for the whole time sequence. Over a whole series of experiments, varying the initial conditions, sputtered tantalum, small grain tantalum, large grain tantalum, single crystal from 2 different orientations. So 2 things to be noted: that the experimental Rayleigh-Taylor growth is about a factor of 5 or so lower than what you'd get with no strength. So we're clearly in the solid state plastic flow regime. It also shows that for all these different versions of tantalum, large grain, small grain, single crystal, different orientations, sputtered grain, that seems to make no difference at all, which was a surprise for us. So we did not see Hall-Petch effect. We did not see small grain structures looking to be harder than large grain and so on. They all looked the same. And so we guessed that the dislocation density was so high that all of the plastic deformation was happening within grains, and never really cared about the grain boundaries and the size of the grains because they were large. It was large compared to where the plastic flow was actually happening. That was the assumption. We've continued these experiments on taken to Nif now, and now I show you Nif Designs. So things are scaled up quite a bit. With the larger energy on Nif, we can go to pressures up to, say, a peak pressure of 8 megabars. Here's a whole series of designs of pressure versus time done by simulations of Sean Prismy, published in Phys Plasmas in 2012, showing we had designs ranging anywhere from a few megabars up, actually peaking out close to 10 megabars. On the lower left plot is the really interesting thing. The higher in pressure we go when we stay in a solid state, the sensitivity to the strength models just gets stronger and stronger. So you see these predictions for Rayleigh-Taylor growth factor as a function of time for all these different models. And it's just an impressive plot. On the top, the blue curve is the prediction. These are for wavelengths of 100 microns in tantalum. Predictions for no strength. So the growth factors are very, very large in the classical regime. And then this whole sequence, really Zarrilli-Armstrong strength model, the growth comes down a lot. Steinberg-Geynin comes down more. Mechanical threshold stress, down more yet. Johnson-Cook, PTW, Steinberg-Lund. And at that time, this is back in 2008, I didn't have access to the multiscale model yet for tantalum, but it would be probably lower yet. And maybe not, probably lower yet. It's down in this range. On the right-hand side, we did the experiments now with the Livermore. We did the experiments and we had the multiscale model. This was done at Nif, I believe, at 3.5 megabars. Here's the experimental data in the solid red squares. And these are published in a, well, certainly in this PNAS article 2018. I think Ye Zhou published this in 2008 as well. But you show the difference. Here's no strength at the top, large growth, then PTW, Steinberg, Geynin, Steinberg-Lund. Livermore multiscale model going right through the data points, very impressive. And before we had the Livermore multiscale, we got used to multiplying Steinberg Geynin because the strength we were getting experimentally was so large. So here's 2 times Steinberg Geynin and 5 times Steinberg Geynin, which was what we had been doing before we had access to the multiscale model. Okay, one plot that's just fun to show. I'm not sure it's interesting so much for high pressure strength, but in one of the experiments we did, just for the fun of it, and this is an experiment in vanadium at omega, we said, let's just keep looking later and later in time and see what happens, see how much growth can we actually get. And so again, this was done, I believe, by Ye Zhou Park at Omega. She went off with a team and was doing these vanadium experiments. And she called about an hour after the first shot when it got digitized. She called up, and I was still in Livermore, and she said, have you seen the data yet? It looks very, very odd. So she called up and showed this image on the upper right, where it looks like in face-on radiography, it looks like a standard Rayleigh-Taylor bubble and spike formation where you have a broad bubble and a narrow spike. But the contrasts are flipped around the wrong way, because bright in this image is low density or little material left, and dark in this image is meaning a lot of material, which would say this would be the Rayleigh-Taylor spike would be the dark region and the bubble the white. But it's just the opposite, because it's the bubble that gets broad and the spike is narrow. So this image was completely opposite to what was expected. And Ye Zhou did a whole time sequence. We stared at this, we scratched our heads, and it finally occurred to us that in fact what we're seeing was a cracking. The Rayleigh-Taylor bubbles were causing the material to actually crack, and these cracks are what we see here in this white region. And so this was, and we published this in a DIMAT proceedings. This was our sort of the first, really, this is before we had diffraction on these experiments to actually measure the phase. This was the first good, strong experimental hint that in fact, even at late times, these foils were staying solid because plasmas don't crack, solids crack. And so we studied this as a platform for studying cracking of samples at very high strain rates if people were interested. That's not what we were interested at the time, so we moved on after putting this conference proceedings article in print, because we wanted to study high pressure flow without this kind of cracking effect. And one last experiment, we teamed up with UC San Diego with Mark Myers and his students. That's been a very productive collaboration for the last 20 years, maybe longer now. And what Mark does with his students is he asks us to recover samples. So we show a recovery fixture that we developed for the Omega laser, where you can recover the sample, bring it home, cut it up, and then look at the recovered sample that's been shock loaded over whatever pressure we dial in. And so shown on the bottom right are images from a shocked piece of, where's the material? Tantalum, here it is. Shocked piece of tantalum where the shock pressure was 220 kilobars. This was put under a TEM. You can see this bar down here is 200 nanometers, so well below a micron. And there were these signatures of dislocation loops, which suggested that the plastic flow mechanism was slip, generation and transport of dislocations. When we turn the shock strength from 220 kilobars to 320 kilobars, we now see these, in addition to slip, the loops, we see twinning bands forming in a whole number of ranges. So based on this result, the Mark Myers team said, we've mapped out experimentally the transition from slip to twinning, and it's around 300 kilobars. And this type of recovery has been done over and over again for a wide range of materials with a series of experiments done by Shitang Zhao, who's now at Berkeley, where we studied the transition to amorphous band formation when we switched to ceramic kind of materials. So it's been exceedingly productive, and a whole series of very nice papers on that. Okay, so that's the end of the physics result. It came to this last talk after our team that we needed to present our problems. So I'm not going to read through in depth all these problems, but I'm going to try and mention what they're about. And I believe this problem set will be emailed to everybody so you have all the details. Okay, so the first one here, in it, let's see, what I want to do is indirect drive laser illumination for a laser intensity of 4 times 10 to the 12 watts per square centimeter for 10 ns. I want to put a package in that is a 5 micron plastic ablator glued to a rippled piece of vanadium. And then the question here is to calculate the ablation pressure that you expect based on formulas, standard formulas that are given, and put the ablation pressure into various units because we are constantly flipping units to be able to match what the experiments are given in. Then I want you to calculate the acceleration of the target, the same target, 5 micron plastic ablator glued to a 10 micron vanadium payload. And I give the ambient densities of the plastic and the vanadium. You can assume the output number is roughly the same, whether it's in the ambient or the compressed case. Then I want you to calculate how far in microns the package is accelerated. And then for a 60 micron wavelength ripple, and assuming this Rayleigh-Taylor dispersion curve for a viscous fluid, where the nu is the kinematic viscosity, I want you to calculate the Rayleigh-Taylor growth rate and the Rayleigh-Taylor growth factors, and then compare this to an equation that says the strength varies as the strain rate times the dynamic viscosity. And based on that comparison, see if you can back out from the viscosity what the actual strength of the material should be. What we called effective lattice viscosity in the previous talk by Robert Rudd. And then the last talk is to actually apply the Steinberg-Geynin model as Rob Rudd was talking about in the previous talk. Here's the model written out. I gave you some actual parameters that match this vanadium experiment. And I ask you to calculate the strength based on the Steinberg-Geynin model and compare it to the strength we inferred in those Omega experiments, the Omega laser experiments done with the vanadium, rippled vanadium. And I think that's that. I have solutions, but I'm not going to show the solutions until Thursday. So with that, Michael, I'm done.
Thank you very much, Bruce. And thank you to all three speakers. We have a little bit of time left today, so if there are any questions, let's do how we always do. Post your questions into the chat window. I'll read them out, and if we start going over time, then I'll bump the rest of the questions to Thursday. So we do have a question here from Felipe Gonzalez. I'm going to read it out. Thank you for the great talks. I have a question for Rob Rudd about the Steinberg-Geynin model. It looks like P and eta equals rho over rho zero are independent variables, but would expect P to depend on eta. The higher density, the higher the pressure. Also, the density depends on pressure and temperature, so the expression for the shear modulus seems to be hard to evaluate. What is P of eta? What is the P of eta dependence, and how does eta change with temperature? Could you comment on how this model is used to calculate plastic work?
Sure. Yeah. So that's a great question. So it assumes a knowledge of the equation of state of the material. So the pressure as a function of the density and the temperature is what the equation of state provides. And so in doing, say, hydrodynamic modeling of systems like this, where there's a substantial compression, it is important to know the equation of state. And so, within the Steinberg-Geynin model, it presumes that you have access to both the pressure and the compression or density. And, at lower pressures, the compression is essentially unity, and you just get kind of the linear pressure dependence. So at that point, it's not too sensitive to the density. But, as you go up in pressure and compression, It does depend on both of them. And so you do need to use the equation of state to get at the shear modulus in those conditions.
Okay, next question is from Amit Misra for Rob and Bruce. At high pressures, like greater than 100 GPa, you mentioned that dislocation density is very high. What is the typical magnitude of the dislocation density? Does the density of point defects also increase at high pressures?
All right, maybe I'll take a first stab at that, and Bruce can chime in. So the dislocation density, of course, we don't have any direct measure of either the density of dislocations or point defects at these conditions. It's not something that anyone has figured out a way of determining yet. Hopefully at some point in the future, in situ diffraction can be used through broadening of diffraction peaks to get at defect densities. But we're not there yet, especially in the context of these Rayleigh-Taylor experiments. However, if we rely on the multiscale strength model, then we can ask, what is the model's opinion of the dislocation density at those conditions? And so, for example, in the 1 megabar tantalum Rayleigh-Taylor experiments that were done at Omega, the multiscale strength model gives a dislocation density that's a few times 10 to the 11 per cubic centimeter. So let's see. So that means a few times 10 to the 15 per cubic meter. So the dislocation spacing is really quite low. So it's a very high dislocation density compared to what you see in typical engineering materials. And so it's because as the strain rate increases, you get a higher saturation of the dislocations. So the saturation comes about by kind of steady state of multiplication and annihilation canceling each other. And so at the higher rates, the annihilation is less efficient. You get higher densities, and so you end up with what is really quite a significant dislocation density, as predicted by these models. Is there anything you'd like to add to that, Bruce?
I think. Can you still hear me?
Yes.
Yes, I think Mark Myers. One time I asked him to see if he could produce a dislocation density in shock recovered samples under the TEM. And I think they did do that, but you can't do shock recovery when you take the pressures up to very high pressures. So if you want to study from a megabar to 10 or 20 megabars, if you really want to study at the various highest pressures, you won't be able to do it in recovery. It might be possible to design an LCLS experiment to go after that. When we went to LCLS, that was not what we were trying to study so much. We wanted to get the mechanism first, so we didn't try. It is a good idea. I think it's worth at least thinking about, is there any way today with combining, what you could do at LCLS versus what you could do on Nif and Omega? It might be worth considering. Could we design an experiment to do that? But I don't think we have the data in hand right now, other than, as you said, the densities are very high.
We have another question here from Felipe Gonzalez. Thanks for your reply, Robert. I have a question for Bruce now. The ramp compression experiments must convert uniaxial stress to hydrostatic pressure, which would mean that the actual pressure reach may be lower. How different is the hydro pressure from the uniaxial stress? Could it be that the systems cannot reach thermodynamic equilibrium because of the short time scale of ramp compression? Can melting be detected?
There's a lot of questions out there. Well, let's see. We can certainly measure melting in the sense that we can see with diffraction, you can see the lattice, curves, the lattice arcs, they go away, and you end up with a very diffuse. So I think we can diagnose melting. The uniaxial compression is, I mean, we're always having to deal with that. So you're pushing in one direction, the lattice squeezes up, and then it transitions to plastic flow, and you get a relaxation of that very odd uniaxial compression. But due to the material strength, it doesn't relax all the way. And so to the extent that you can do diffraction and measure diffraction off the different directions, you know, the direction that you apply the stress to gets compressed more than laterally or perpendicular to that. With diffraction, you can try and measure that and use that as a independent measure of the strength of the lattice off of, say, single crystal, and you can study experimentally what he's asking about. It doesn't go to a pure, 3D unrelaxed state if you have strength still on. So there's always going to be a little bit more compression in the direction of the uniaxial compression until it melts. Sometimes the materials are not so strong, and so it gets harder to actually distinguish the remnants of the 1D compression, but it's there.
Okay, just for fairness sake, I entered my question into the chat box as well. So my question is, can your in-situ diffraction setup detect twinning, for example, in initially single crystalline samples?
Yeah, we did that at LCLS, and then we followed up with experiments at the Omega laser once we knew how to do it at LCLS. You can, just by scattering, if you have a very nice, well-characterized backlighter where you can control its directionality, you can distinguish twinning from slip. And there's a very nice Nature article in Nature by Chris Werenberg. I think the date was like 2013 or 2015. We went to LCLS to do it the first time because we were worried we wouldn't be able to see that dynamically. We'd been seeing that in recovery with Mark Myers for quite some time. But to look for that dynamically was hard. We went and did the experiment at LCLS and had there's a very nice Nature article that describes that with Chris Werenberg as the first author. And then once we saw what to look for, clearly, we went to Omega and did it there as well. So you can study slip twinning dynamically.
Okay, I have one more question from myself. The Rayleigh-Taylor instability tests you showed were extremely high stresses. So is there a threshold stress below which you do not see the RTI?
Yeah, except that our pressures and our stresses are so high that, let me think a second. I don't think we've ever done a Rayleigh-Taylor experiment in the solid state where we saw no growth. Some of the growth is low, some of the growth factors were 2 or 3. So, but I don't think we've ever done a case where we think the growth factor was flat out 1. If Jesus Park's on the line, she may remember, because we've done many experiments in many different materials. But I don't recall ever doing an experiment where there was no growth at all. In the plastic sense, I mean, you can imagine a scenario where there's elastic deformation, then when you turn the drive off, it goes back to its initial state. I don't think we've ever seen that.
Okay, thank you. I see that there is that Robert posted a reference to the chat box that says the twinning was detected by diffraction in Werenberg et al. In Nature 550, 496, 2017. So for anybody interested in that reference. Question from Yupeng Zhang. May I say we can use RTI to characterize any material as a standard test approach?
Well, we certainly use it to test our models heavily here at the lab. Rob, do you want to say anything to that?
Because the reason I ask this is that in the material science community, usually, okay, sorry. in material science community, usually we do not use this sort of method. Usually we use indentation or tension, compression, this sort of method. So I'm just curious about, can we use this as a standard way to characterize, especially for some soft materials that is not convenient to do by the conventional tension or compression test?
Well, we do that exactly. I mean, that's exactly why we developed this at the lab. And we do study soft materials and hard materials. I mean, I showed diamond, but I also showed lead, and we're studying tin right now. So they're both very, very soft. But as you gently ramp up the pressure, they very quickly become very, very strong because you go through several phase transitions. So we're doing this precisely for that value.
Okay, thank you. So actually, the soft material I'm considering is about like hydrogel or some like other polymers that are much softer and something like that.
Well, we've studied polymers and plastic and so on, mainly for just studying the Rayleigh-Taylor instability with the absence of viscosity. But if it goes through a phase transition, then its character will be very different. I mean, that's why we do these at the lab, is exactly for what you said. It's just that we were generically interested in high pressures well above a megabar, motivated partly because of our ICF, inertial confinement fusion, laser fusion effort, where we're imploding capsules, but the pressures are very, very high.
Okay, thank you.
Okay, I don't see any other questions coming up in the chat box right now. So we're almost at the end of our time. I suggest we take a break. As Bruce mentioned, I will be sending out a copy of the homework assignments, the problems that were given. And then we will be back online on Thursday, 1 hour earlier than today. So 11 a.m. Pacific, noon Mountain, 1 p.m. Central, 2 p.m. Eastern, to go over those problems together. Okay? Thank you very much again to all the speakers and everybody who signed on.
Good.
Have a great day.